Okay, welcome back everyone to the Python tutorial seminar series. Today, Anissa Zacharias will be covering the package Matplotlib, and I'll hand it over to her in a second. But before we begin, I need to review our code of conduct. By joining this Zoom call and participating in the tutorial seminar series, you've agreed to adopt these values and engage in respectful communication only. Any inappropriate remarks will get you removed from the chat. In the chat will get you removed from the call by one of our co-hosts. As always, the seminar is only an hour long, so if you need help, we will try our best to provide it for you. Just sit back, relax, and we'll get you back up to speed as best we can. And some learning resources I would like to direct you to are the Python and Matplotlib documentation, as well as Stack Overflow. Today, we have content that's been posted on GitHub, on Anissa's GitHub, and I'll put the link to that in the chat, as well as the Geocad examples gallery, which is a collection of geoscience plotting examples that you might find very useful for your specific applications. And with that, I will hand it over to Anissa.
All right, hi guys, I'm Anissa. I work with the Geocad team, and this is going to be a Matplotlib tutorial. Hopefully I can share my screen. Let's see. All right, can you guys see that? Okay, I'm going to assume yes. All right, so before I start, I just want to say that this will in no way be a complete tutorial. I'm pretty sure we could do an entire series just on Matplotlib itself. So in this tutorial, I plan on covering kind of things to get you started. And in the example notebook we're going to clone momentarily, you will see links to many more examples and many more tutorials that you can go and look at your own time. So as far as setup, what we're going to do is first we are going to clone the repository that Julia mentioned just a second ago. So to do that, we're going to navigate from the terminal into a directory where you'd like to put it. I generally put all my tutorials in my documentation or my documents folder. So I'm going to go to Documents, Tutorials, and from here I'm going to make a new directory called Matplotlib. And I'm going to enter that directory. And so from here, we're going to clone the repository that was just talked about. We are going to do this with Git Clone, and then link to this tutorial repository. So it's at https://github.com, and my username, which is Anissa111. And then the repository is called Matplotlib tutorial. Matplotlib, sorry, dash tutorial. All right, so now if we look in this directory, we have a new directory that I can cd into called Matplotlib tutorial. And you're gonna find a bunch of files in there. We're not going to touch any of these right now, but we are going to pull up Jupyter Hub. So to do this, you'll see that I'm in my base conda environment. You can look at all your environments by going conda env list. And the one that I set up on the previous Jupyter Lab tutorial is called Jupyter tutorial. Yours might be called something different. You just need to activate an environment that has Jupyter Lab installed. So I'm going to go conda, activate Jupyter tutorial. All right, so now that I am in this repository and have the right conda environment, I'm going to start Jupyter Lab by typing Jupyter Lab. And now for this terminal, you need to keep it running, but you can just kind of hide it in the background. All right, so this is populated with the stuff from when I was playing with it before, but basically what you're going to do is from here, you're going to make a new notebook. You can follow along in the notebook that I've already created. I'm going to be typing everything out in case you want to type it out with me, but just so you know, there is a pre-made notebook with everything we're going to be covering and like cool little links to documentation and whatever you could want. So
Excuse me, yes? Anissa, there's been a request to slow down just a little bit. Can we give people a little bit of time to catch up?
Yeah, absolutely. Is there anything I need to go back and cover?
If there's anything specific or anybody's stuck, please post it in the chat.
I'm seeing Matplotlib and Numpy. Yes, we can load those from the Jupyter notebook directly, which is in the example notebook. If you want to do something like conda in, sorry, I have trouble typing in front of people, install Matplotlib and Numpy. You can do something like that, or you can, from a terminal with this environment activated, you can install it from there. A history of my terminal. Sure, I can do that. Let's see. Let me just scroll back up because I can't actually enter new commands when the Jupyter Lab is running. So from the beginning of the tutorial, we went into a new directory and we did Git Clone. The link to that should be posted in the chat by one of my co-hosts. And from there, we then entered into the directory that created. And we looked at our conda environment list to see all of the environments that I have. We found the one that has Jupyter Lab installed. We activated it, and then we launched Jupyter Lab as a summary. All right, so I'm going to keep going. If there's any more things, please talk about it in the chat. I do have the chat pulled up, but I don't know how often I'm going to be looking at it. Okay. So the first thing that we're going to do in this notebook is, again, you could do conda install from here if you would like. And so the first thing we're going to do is we're going to use a Jupyter Lab magic command. So this magic command essentially allows Matplotlib plots to be displayed inline as we go, and we're just going to stick it right at the top, Matplotlib inline. There are different versions of this that you can have like interactive plots or have it not pop up inline, but this is by far the easiest for this tutorial. So we're gonna go ahead and run that. Now we're going to import Numpy and Matplotlib, which are the packages we're going to be using here. As np and import matplotlib.pyplot as plt. And you'll notice we didn't actually import Matplotlib directly. We imported something called pyplot, which is the plotting interface for Matplotlib. So run that. If you encounter errors here, it is because you have not included Numpy or Matplotlib in your tutorial. You can go ahead and run the conda install and then restart your kernel if you would like to use it in here, or if at any point you can get stuck, you can always follow along in the pre-created notebook. All right, so just to start us off, I'm going to pull down this image, which is in the pre-created notebook, and it's essentially just the anatomy of a Matplotlib figure. You can see there's a bunch of different things you can add. X labels, figure itself is the entire figure. There's titles, grids, splines, a lot of different options. So I'm going to put that back away. And so what you need to know about Matplotlib figures is that it has two core objects, figures and axes. Figure keeps track of the child axes, which can be one or more, and that essentially all things involved in Matplotlib are actually called artists. This is a bit more complicated than we need to get into right now. Almost everything is an artist, including like the figure itself, the axes, as I mentioned, and stuff as like if you want to add additional text or a legend. But for now, just worry about figures and axes. So we're going to start off by making a basic plot. To do this, we're going to use NumPy to define two little tiny nonsense arrays, basically, called x and y. And I'm going to do numpy.a range, like a range, but without an R. And you don't have to use these same values, but just any sort of arrays that have the same dimensions will do for just now. So I'm going to do that, and then y equals numpy.a range. And 1, 3, 2, 5, and 1. That's fair. Let's see. What did I do wrong?
I don't think you want to use
array in there.
Yeah, it's array instead of a range.
Yeah.
That's a very good point. Thank you. I think we do use a range later. Thank you for catching that. Yeah, that worked. So now we're going to use Matplotlib to make explicitly a figure, axes onto that figure, and then we're going to plot onto the axes. So first we're going to create figure. And we do this, I'm going to call it fig, by calling plt, which is from Matplotlib pyplot, and then figure. And this will create the figure for us. And now, since this is a really basic plot, we're actually not going to make the axes, but we're going to grab the axes from the figure. And we do this with axes. And we do this with axes equals plt.gca, which stands for get current axes. This will just allow us to reference the axes when we need to plot. And so now we're going to plot onto these axes using axes from up here, and then plot. And we're just going to give it the x and the y. And I'm going to be adding semicolons to the end of it, just so that it doesn't print out weird stuff. But again, it's perfectly fine. For instance, if I didn't run it with that, it would just print this little thing up here. But if you see me adding semicolons in Python, that's why. So that's it. You can see our points here, 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 and here. But this might seem like a lot of work just to plot these two little things. And in fact, a lot of Matplotlib calls will make the figure and the axis for you implicitly. So we could also, to do the same exact thing, could have just done plt.plot and then x comma y. Just one call. But a lot of plots you're going to making are a lot more complicated than this. But if you just want a really quick way to look at what you got, that'll do it. I believe you actually covered that in last week's or 2 weeks ago NumPy tutorial. All right, so also, before I get started on more complicated examples, I just want to say that there are a ton of different ways to make a given plot and its reference, and there's no right way. There might be better ways, but I'm just going to try and show you a variety of ways to do all these different things. So this is a pretty boring plot we made. It doesn't have any titles, it doesn't have any things, it's just a little blue line. So let's make something a little bit more complicated. I'm going to make subplots this time, and I'm going to include this original image right here on the left and something a little bit more, I wouldn't call it pretty, but styled on the right. All right, so we can do this by a Matplotlib command called subplots equals plt.subplots. And then by supplying the number of rows, n rows equals 1 and n calls equals 2. So this is just saying I want 1 row and then I have 2 things in that row. And you'll notice that I did figure and axes as returns for this. And so I don't have to do anything to get the current axes, it just returns it automatically. And so the interesting thing about this is that it actually returned axes as a list. So to plot onto the axes, I actually need to refer to the first axes with 0 and the second axes with 1. So on this first set of axes, we're going to plot the exact same thing, plot x comma y. And on the second set, we're going to do plot x comma y again, but we're going to provide some additional inputs. So let's see, we want to change the line color. Let's make color equals red. And let's make the line style something like dashed. And let's add markers, because as you can see, it's just kind of a line, and we can add markers to these points. And let's make them something silly like stars. And let's make the marker size, let's bump that up. Marker size equals 25. And we can even change things about the marker, like we can change the face color. And let's make it black. There are also many different ways you can specify these inputs. You'll notice some things I'm writing out, some things I'm shortening. You can go to the documentation listed in the pre-made notebook to find like all these different examples of what you can and how you can put it in. Here, K actually stands for black because B is blue. But you could also, of course, just type out black. And we're gonna change the marker edge color. And we're gonna have that be blue. So when we run this, we get a little figure, and this is a very ugly plot, but it is a plot that looks different. And I just did this to kind of show you guys all the different things you can customize, or some of the more the more common things that you could customize when you make a plot. All right, so, oh, before I move on, you'll also notice that this is kind of squished, and it's because if you look above it, they're about the same size, and it's because I never specified a figure size, so it's always putting it in the same little block. All right, so now that we've done a basic little plot, we're gonna move on to a two-dimensional plot. I'm just gonna separate this out in my notebook. I'm gonna do 2D plot. Oops, plot. I'm gonna make that markdown, make it real big and pretty. All right, so a lot of geophysical examples, of course, involve two-dimensional data plotted over some sort of map or whatever have you. So first, we're gonna use Numpy again to create two arrays. And here we actually are gonna use a range. Sorry about that before. So we're gonna redefine X and Y. We're gonna have X equals np.a range. And we're gonna have it go from -3 to +3. And we're gonna have it move in increments of 0.05, just so we get like a really fine, or a kind of fine resolution in there. And we're gonna do the same thing for Y. np.a range, -3, 3, and 0.05. 0.05, yeah. And so now what we've created is kind of two just like one-dimensional arrays, but we actually want them to be on a sort of grid. So what we're going to do is we're going to make a capital X and Y, and we're going to use something called np.mesh grid. And we're going to give it the X and Y we just created. And what this kind of does is it creates a grid using, it assumes one is the X and one is the Y in the order you give it, and it fills in all these values. And with this, what we're going to do is we're going to make a variable Z, which is going to be what we're going to plot over this grid, like the actual data. We are fabricating this data, so it's not going to really mean much, but it is going to be two-dimensional and it is going to have pretty colors. So for this, I just chose some trigonometry stuff. Numpy actually has good trigonometry functions if you ever need them. And we're going to feed it the big X and the big Y. All right, and now we're going to run that to make sure I didn't do anything silly. All right, cool. And so now I'm going to go over kind of 3 different ways to show two-dimensional data. The first, I'm going to make a set of figures and axes using plt.subplots again. And you'll notice that I'm not actually feeding it anything, and that's because subplots can make a 1-by-1 subplot if you don't give it anything, which is really useful if you just want to get the figures and axes as one thing. Again, I'm just showing you a bunch of different ways you can do things. And now, so we're going to define our output to our plotting function, and we're going to plot it on the axes we just created, and we're going to use a function called imshow, which is defined to show, like if you have a matrix of different values and it's actually an image, you can plot it using imshow. And we're going to give it Z, the data we just created. All right, so that's our little plot. And it looks trigonometry-y, it looks sine and cosine, which is exactly what we wanted. But you'll notice that the X and Y are really off. We gave it -3 to 3, and it's going not that. And this is because from the mesh grid, it doesn't actually pass on the range information. So what we need to do actually is from the imp show is we need to provide it the range that we actually intended to be the data points over, because this is the number of physical data points we created, and that's not actually reflecting the range that we wanted it to be over. So let's try this again. We're going to redefine m as ax.mshow, give a z again, and then provide an additional argument of extent. And here, it's just one big array, and it's the first, which is -3 to 3, and then again, -3 to 3. I believe it's an x, y, but I could be wrong about that because I made a square. All right, and to make the figure pop up again, we're just gonna type fig right below it. All right, so that looks about right. We have 3, -3, and -3 to +3 with 0 right in the middle. So that's the first way to kind of make this, but of course, there are many more things that you can add to mshow to have it do different things. For instance, we can't really tell what values are going on in here. And it looks really smooth considering we only gave it a 0.05 resolution. And this is actually because mshow by default uses an interpolation. The interpolation it uses by default is, I believe, anti-aliased interpretation. But there are a bunch of different methods you can use. So I'm just going to real quick show you some of the options that you can feed into mshow. Axis. Give it z, and we're actually going to turn off interpolation. None. And we can also change the colors. One that I'm particular to is something called cool warm. And this is just changing the color map that we use to plot it. So it's not going to be like yellow and purple. It's going to be something else. And again, feed it the extent. -3, 3, -3, 3. All right. And oh yeah, we're going to add a color bar so we can see what values are actually going on in here. So we're going to call this C bar, and we're going to call it from the figure. And the command is called color bar, and we're going to feed it the image, which we just created from mshow. All right, and fig. All right, so one reason I chose this color map in particular is because it's a diverging color map. In the pre-created notebook, there's a link to a bunch of different color map options, and if you don't like any of those, you can create your own. So what this does is you can see it goes from red to kind of pink, and then at 0, it hits to white, and then in the negative values, it goes to blue. Say you wanted it to diverge at something else, you could also set that value, like if you wanted it to diverge at sea level. It doesn't have to diverge at 0. But yeah, and you'll also notice, I don't know if you can see this across Zoom, but it is a little blocky. And if you look really closely, it's no longer blurry, it's no longer really smoothed out. And this is because we turned off the interpolation. But of course, this is not the only way to display 2D data. Oh, excuse me. And so for this, I'm going to create subplots again and show you a couple other methods. So I'm going to make 1 by 3 subplots. And again, I'm going to overwrite figure and axes. And I'm going to have this equals plt.subplots again. And rows equals 1 and calls equals 3. Oh, also, if you're not familiar with this subplots thing, it's actually a fairly new kind of like suggestion, best practices by Matplotlib. When I was first learning how to do this, we did something called like add subplots. But yeah, this is the most recent version in case you weren't aware of that, because I certainly wasn't. All right, so now we're going to plot the same mshow on the first set of axes, mshow. So axes reference 0 again. And then mshow, mshow. Actually, I'm just going to pull it from right up here. Well, okay, yeah. Axes.mshow. And I'm not going to use a color bar in this one just because there's a bunch of them, and I'm just not. I'm not going to use a color bar on this one. And let's actually add a title to it. So axes 0 dot set title. oops, title. And we're gonna label this one ImShow, just so when they show up, we can see really clearly what's what. And then, so the next one is actually called contour. All right, and so on this one, we're gonna plot it on the second set of axes, which is axis one dot contour. And for this one, we're gonna give it the same Z. We're gonna have CMap equals cool warm again. And we're gonna give it the extent, which I'm just gonna pull right from up here. All right. And again, we're going to set the title. For the third one, it's called contour F. And we're gonna do this on the third set of axes, contour F. We're gonna feed it Z. Actually, it's the same exact call. I'm just gonna pull it from right up here. And again, we're gonna give it a title, which I am repurposing again from above. All right, so. Yep, okay, so plt.subplots, not plot.subplots. Yeah, there we go. All right, so you'll notice a couple things about this. You'll notice that the axes from ImShow are square and the other ones are kind of distorted, even though they run from -3 and -3. Sometimes this matters, sometimes it doesn't. But for here, I'm gonna say it matters because this kind of looks funny. And also you'll notice that for ImShow, the kind of dark red is actually at the bottom. And for the other two, the dark red values are at the top. And this is actually because the plots we created up here are wrong. ImShow actually assumes that your origin, your 0, 0 of the array, is actually at the top left corner because it's for images, which would kind of make sense. If you're defining an image, you wouldn't start from the bottom right corner. So we do need to flip this around, and there's actually a really fast way to do this. So let me actually just go ahead and pull this entire thing from up here. We're gonna redo it. Let's put it down here just so we don't have to type everything out again. And then what we're gonna do is to fix the ImShow, what we're gonna do is something called origin equals lower. And this will set the origin from instead being at the top left corner to the bottom left corner, which will make it physically make more sense and be correct. And to set the aspect ratio of these so that they're not all squished out and instead of being square like ImShow, what we're gonna do is for each set of axes, we are going to call something called set aspect. And we're gonna pass it in equal. And I'm gonna do the same thing below, except for making sure to put a 2 in there. And then again, we're just gonna call thick. Yeah, so this looks much better. As you can see, the ImShow flipped right around and all these look nice and square. So these are different ways you can plot 2D data. It is, I'm sure, not all the ways, but it is the most common ones that I've ever used. Other things is you can plot contour on top of contour F by just including 2 things on the same set of axes. There's tons of stuff you can do. Again, check for the documentation listed and just through Google if you want essentially an endless version of things to do. So the last thing we're going to do here is we're going to do a geophysical example, and we're going to plot the Southern Oscillation Index. I'm a software engineer by default, and if I say something wrong that's sciencey, I apologize. I think I have everything right, but yep. And before I get into this is going to be a shameless plug for the Geocad examples repository. This is actually an example that I shamelessly stole and repurposed for this. The Geocad examples repository has a bunch of way more complicated examples than this and cover a bunch of geophysical examples for a lot of the original NCL documentation plots, in case you're curious, and even more. So the links to that are both in the slides at the beginning. And oh, it looks like somebody put it in the chat. Thank you, Julia. And in the pre-created notebook. So to do this, what we're actually going to do is we need some data. And there's more complicated ways of getting this data, but I have simplified it for this. And we're going to use a Python module called Pickle, spelled exactly the way you think it is. Let me make a little separator like I did before. Mark down SOI for Southern Oscillation Index. All right, so we're going to import Pickle, P-I-C-K-L-E. This should be automatically in everybody's Python thing. It comes like by default, kind of like math does. So you shouldn't need to import it. If it goes wrong, I wouldn't even know what to do. Google it, I guess. Don't know why I said that. So right before I talk about, or before I use Pickle, what it does is it takes NumPy objects, like NumPy arrays are specific objects that you create yourself, and it turns them into a binary file. And so you can read right into the binary file and you get NumPy objects, which is easier than like if you have a really complicated setup, having to like read in the data and then create the NumPy objects again. But the thing about Pickle is that Pickle files are not secure. They are just binary files and there's no sort of text that goes into them. So when you unpickle a file, make sure you trust what's in it. All that's in this Pickle file is NumPy arrays. So I can unpickle it and you can see what's in there. All right, so to do this first, we are going to open the binary file. So to do this, we're gonna do something called in file. That's just what we're calling it. And we're gonna use open. And then the binary file in the repository that you should have cloned is called soi.pkl. It doesn't have to have that ending. That's just what I did as kind of like a standard. That's what I've always used. And we're going to give it the other option of R, which stands for read because we're going to be reading it, and B because it's a binary file. And then we're going to get the data out of this file. You can only really pickle one object at a time, but objects can be easily combined in Python. So it's essentially like pickling more than one. But so I have pickled a date variable, a SOI variable, and a decadal SOI variable, which is the SOI. And so these are all packed into one array in the binary file, and I'm just going to pull them out exactly like this when I load it in. So I'm going to, from Pickle, I'm going to load and then give it the in file that we created up here. In file. Spelled that wrong. In file. Yeah, okay. And then we're also just going to close the file as a matter of good practice. Python would probably do this for you, but it can lead to a bunch of weird errors if it doesn't sometimes. So it's always really good habit to close the files you open. All right, so that looks like it loaded in, but let's just make sure. So we should have something called date. Yeah, and it made a little NumPy array. You'll also notice that these dates are fractional, and this is because it makes it really easy to plot. In the original Geocad example, which is linked directly to this particular example from the pre-created notebook, there is actually a little fiddle-in that goes on. It converts the dates to fractional just for like plotting purposes. And it is frequently a problem where you need to convert date formats in order to plot along like an axis. So it doesn't, like, how do you plot May 2nd, you know? So if you want more information on that, I'm not gonna go through it here. I prettified it before I pickled it, but it is in the Geocad examples repository if you wanna go look at that. All right, so now we're gonna see what we got. I'm gonna just delete that real quick. And so I'm gonna do figure equals plt.figure, going back to one of the first ways that we made figures. And I'm gonna do axes equals plt.gca, forget current axes again. And now on this, I'm going to plot the date as the X variable and the SOI as the Y variable. I'm gonna give it a color of black. And I'm actually gonna make this one a little thinner because I know what the final value is gonna look like, or I know what the final creation is gonna look like. And I'm also gonna give it a label. I'm gonna call it SOI. And then on the same set of axes, we're gonna do another plot and we're gonna give it the same date and we're gonna do DSOI. Color equals black again. Actually, no line width for this one. And we're gonna give it a label of DSOI. All right, so I'm gonna pause here if you need to catch up typing that. All right. And actually, right before we run this, we're going to add a legend. This call is actually really cool. It just pulls in the labels that you've created above for the set of axes, and it makes them into a little legend. I'm not going to get into like more complicated legends, but you can move them around. You can format them all sorts of ways. But for this one, this is how you add a legend. All right, so I'm gonna run this. Right, so that figure, it sure is a figure. It looks kind of ugly. Can't really tell what's going on. The y-axes don't look centered around 0 as Southern Oscillation Index is you want to look for something when it goes above and below 0. Again, not a scientist, sorry. And so we're going to make a couple adjustments to this plot. This is actually a similar process to what I would go if I was making a plot to try and display some data. I would kind of just like plot it and then add things to it as I go. So let's real quick just add a horizontal line through y equals 0. And we can do this with something called AXH line, axes H line, horizontal line. And we're going to give it y equals 0 so that it goes through y equals 0. And we're going to make it gray. EY. I don't know if AY would work. Let me put AY and see if it does work. And then we're also going to bump the line width down a little bit. 0.75. And this is in points, by the way, 0.75 points. It's not like a percentage or anything. And then we're going to recall the fig to make it show up. All right, so that looks a little bit better. GRAY apparently does work, figuring things out on the fly. And now we have a little line that goes through there, but it's not quite centered. This doesn't look very good. It's kind of going up and down really fast. So let's do something else. Let's square up the y, square up the y axes. And so it goes from like -3 to +3. So it kind of like squishes everything down and makes it a little less jaggedy. And let's also set the figure size to kind of stretch it out a little bit. So what we can do is from axes, we can go set y lim and give it -3 and 3. And then we're also going to go axes set x lim, and I actually don't need to set the x lim for those one. It's from 1800 to 2000, so never mind on that. But we are going to set a figure size. So figure dot set size inches. It is by default in inches. There's not anything like set size centimeters that I know about. And we're going to make it 8 by 4, which sounds really large, but it isn't as big as you think it might be. Oh, it's 8 by 4. You know what I mean? It doesn't show up as big as you think it might. And let's again call fig, and let's see what happens. Yeah, so that looks much better. I can see much more clearly what's going on. It's a little bit more stretched out, but I still really want to be able to see what's above and below the y equals 0 line. So I'm going to do something called that's from axes called fill between. And I'm going to, if I can spell, between, which is going to essentially take like 2 values and like a line, and it's going to make, it's going to fill it with a color. So above the x-axis, or sorry, above y equals 0, I'm going to fill it with red, and below it, I'm going to fill it with blue. All right, so we need to give it exactly what line we're talking about here, not by giving it the line directly, but by giving it, again, data and SOI, so it has the x and y values. You don't have to actually give it on a line that you've already created. For instance, if I had like another line going through here and I didn't actually have the line itself plotted, but I wanted to like fill it, I could do that too. And now we're going to do something called where. And we're going to say where SOI is greater than 0. We're going to have color equals red. And now that was just half of it. We can't do both at once. So axes dot fill between again. Again, date and SOI. And then instead of greater than 0, we're going to have SOI is less than 0. And we're going to have this be blue. All right, and now we're going to do a fig again. Yeah, so that looks pretty good. This is the figure that I would be happy with, and it's also the figure that's in Geocad examples. And But one thing is very clearly missing, and it's titles and labels. So right before we get done, also the last thing I generally tend to add to my things, when I create them, we're gonna set title on this axis in particular. You can do it from the from like just plot in general, but it actually acts funny in Jupyter notebooks, and you have the original plot and then like a blank one with it on it instead. We'll get into that. But so we're gonna call this Southern Oscillation Index, and another one, set X label. And this is year, might be pretty obvious, but let's label that anyway. And set Y label, also pretty obvious given the title and all the labels, but that's a Y. And let's call let's call the fig again. All right, so that looks pretty good. The figure title looks a little bit small. So I'm just gonna go back and I'm gonna go font size 15. I think the default is like 11 or 12. Should have looked it up, but I totally forgot. So 15 will make it bigger. Yeah, so that looks good. And I'm calling this the final version of this plot. So this is all well and good, but the majority of time, at least I make plots, I'm not actually making them in Jupyter notebooks. And the feel of making a plot in a Jupyter notebook and a Python script actually feels pretty different, at least to me. So what we're gonna do is we're gonna convert this last example we just made into a Python script. Actually, I've converted all the examples we just did into Python scripts that are already in the repository, but I'm gonna focus on this one because we just did it. So you could open a new file and call it SOI_plot or something. It's already in there. You can copy and paste it into a new one if you want, but here it is. This is almost exactly the same commands we just did. So we import everything, we get the binary file, we unpickle it, we close the file, and then things start getting a little bit different. So for instance, we called the fig size directly from the figure, which is, if you already know what's going on, something that you can plug in ahead of time so you don't have to like go back and add it after the fact. The legend we call a little bit different. For example, we call it from PLT. In Jupyter notebooks, if you call things directly from PLT, it gets a little mad. It's the thing I talked about before, where it would kind of create like your original plot and then a new set of axes with stuff on it. Not sure why that does that, but yeah. So a lot of things in the Jupyter notebook I actually called from axes or figure instead of doing it from PLT like I would generally do in scripts. And this is a major difference too. So it's the same thing. We can just call it directly from plt.xlabel. So instead of axes set_xlabel, we can just do plt.xlabel. Again, so many different ways to like reference and make the same exact plot. But the primary difference in plotting from a script versus plotting from a notebook is you have to call plt.show. Nothing, it'll make the plot, it'll be like in the internals or whatever, but it won't actually show up until you hit plt.show. So let's go ahead and from, I forget what this is called, from this, let's create a little terminal. And this should be in the same directory as we were just in. So yep, we're in the Matplotlib tutorial. And this is a pre-created notebook, excuse me. And so we're just gonna do a real quick Python and then SOI plot. And yeah, so it popped up a separate little window here instead of plotting inline like we were doing with the Jupyter notebook. And this actually has some interaction with it. It might display differently depending on what kind of computer you're on or what kind of like display. For instance, when I was using like Linux machines, it didn't show up exactly like this, but it did like show up in some kind of window. So from here, you can see there's a bunch of different stuff you can do. When you hover your cursor over words, it actually shows your X and Y coordinates like on the plot and like on the X and Y axes in real time, which can be really useful. Or say you're not exactly sure from like what part of a data set you want to plot, you can do stuff like, oops, got to highlight it first. You can like zoom in or like, you know, what's that? And like you can zoom in really far. Yeah, by the way, if you zoom in too far on like fill between, it gets a little silly. But like now we're all the way in here. So what do we do? Like hit home, we're back again. And you can also do things like adjust the white space around like figures. You can do a bunch of stuff. You can also absolutely do all this from scripts, but like if you just want to see like what's going on real fast, you can do it. And you can also from here save it. And so we can do that. But of course, like what if you're on like Casper or just some sort of like remote system and you can't directly do this? In the plot or in the scripts, I have commented out something below plot.show. Oops. And so we're going to comment out plot.show and we're going to do plot.savefig, which is kind of the same thing as plot.show. Instead of showing it to you, it just saves it as whatever you tell it to. So for plot.savefig, I am naming it soi.png. And if I run this again, did I save it? I did not. All right, so, and then it'll actually, yeah, there it is, soi.png, which you can open from here. And look, it's the same exact thing. There's no interaction because it's a pre-made PNG, but you know. So yeah, there's, for all of them, in fact, there's the 2D one we just created and the basic plot we just created, and you can go through at your own leisure and like look at the difference, but it's essentially just you can call things from plot directly and you need to call plt.show at the end. Yeah, that's the Matplotlib tutorial. In summary, what we covered is we covered the anatomy of a figure. We looked at how to create a basic plot using several different methods of figure and axes arrangements. We looked at how to make subplots. We looked at how to make two-dimensional data. We looked at color maps. We looked at a geophysical example with a several shameless plugs Geocad examples repository and advice to Google things if you want more examples. And yeah, that's the Matplotlib example tutorial. I think we have about 10 minutes for questions. I'm not sure if there's any that came through on the chat or if I'm forgetting to do something incredibly obvious. Let's see. Let me stop sharing. Yeah, so are there any questions? I am seeing something about dots per inch. Yes, I don't know why I stopped sharing. Yeah, there's actually something, I think it's just DPI if you say fig. I am Googling this really quick. DPI.
Yeah, you just specify DPI equals
DPI.
whatever number.
I'm not sure I have save fig linked, but a lot of the documentation that I linked has like all the different inputs that you can have for a function. I did not cover them all because there are a ton. But yeah, you can also set like the white space around it to be smaller. You can set the background to be transparent. You can set a ton of stuff from savefig. I'm seeing something about Pickle. Yeah, so, okay, so Pickle, what it does is, say you have like NumPy objects, like a NumPy array, like there is no, like you can't save a NumPy array, you know, you would have to take the values out and save the values. And then when you want it again, you could read it back in as values and then put it in a NumPy array. What Pickle does, it's like a Python thing that allows you to convert the object directly. So in this case, the NumPy arrays, and save it as bytes that then when read back in through Pickle goes, oh, this is a NumPy array, and it's it just makes it automatically for you. This was a really basic example. We probably didn't need to use Pickle, but just to introduce you guys to it, and because it's super convenient, because it, it automatically made the NumPy arrays for me. It was all just right there. So yeah, that's Pickle. But so when you do a Pickle load, you are just loading in a binary file, and there's no check to see what this binary file is when you read it in. So make sure if it's a Pickle file you created or one that you trust before actually reading it in.
And you should also notice that if you use Pickle to save or load objects that are special objects defined in, for example, a third-party package like NumPy, you will get an error if you do not have those third-party packages installed. So that's another
Yes.
complication with Pickle. There's nothing in the Pickled file that's going to tell you need these third-party packages installed in order to load this. You'll just get an error. And you may be able to decipher what package you need to install by the error, but it does have some limitations.
Yeah, I'm seeing Anderson in the chat saying that NumPy has a save method specific for NumPy arrays, and like, yeah, that's true. I just thought of Pickle first when I was making the example, honestly. Yeah, we were trying to find a way to get around. We actually have something in Geocad where we load the data file from a Git repository, but it involves several Geocad packages, and we didn't want to use those in this example for like simplicity's purposes. Are there any other questions?
When someone asked the question whether or not you can use Pickle to save and load lists and tuples and stuff like that. Yes, Pickle is for any Python object.
Yeah, it can even be like objects that you like defined yourself. Please stop me if I'm getting into things that aren't technically true, but I'm not a Pickle expert. But yeah, it will save anything as long as you have like the right framework when you load it back in.
Yeah, if people are familiar with issues with parallelism, for example, you can actually use things like MPI or other types of communication like TCP or something like that. And you can pickle an object into bytes, and you can actually message the object to another machine, and the other machine can unpickle it and use that object. So in other words, you can actually message around actual Python objects, not just data.
Yeah, it's super convenient. Yeah, Julia is saying in the chat, I just want to say it out loud. You can save in multiple different things other than PNGs. I just did PNGs because that's just generally what I use. They can save as other things like PDFs, JPEGs, SVGs, whatever you need if you need a specific file type coming out. Yeah, the bbox inches equals tight. It does remove a lot of the white space around it. Yeah, there's a ton of different stuff you can do with savefig and actually everything. A shared color plot that totally exists. It's a little bit of a pain in the butt. I shouldn't say that. It's not a pain in the butt. It's not something I wanted to get into here. You can do it, yeah. Yeah, I'm pretty sure if you just like Google shared color plots or shared color bar for subplots, it would come right up. Yeah, thank you for that link. All right, is there anything else? But yeah, also Geocad examples does that several times. Let's see. Class methods versus instance methods. Not that I can think of off the top of my head. If anyone of the co-hosts or somebody in the chat wants to jump in and say anything that I'm missing. I generally always call things from PLT if I can. Sometimes this will get a little tricky if, like, for instance, there's multiple axes going on or like different artists that I'm trying to reference. Referencing things from the artist directly is the easiest way to make sure that it ends up where you're trying to get it. Again, stuff gets like, if you're making like a big old grid of like a ton of them, calling PLT on something, it will get the last axes that you were working on. For instance, like if you're doing like axis 0 dot plot, and then right below it, you did like a PLT call, it would reference the axes created just above it. But if you're like switching between axes trying to do stuff and you call PLT, it might not always end up where you think it might. Yeah. Okay, cool. I'm glad that was helpful.
Yeah, I think calling instance methods, which of course means you have to hold on to all of those instances that you create, gives you a lot more control and precision, I would say.
Yeah, that's a good way of putting it. Yeah, there's also, I think, some stuff that's like almost impossible to do from PLT that you actually need to reference the axes for, or like the figure itself, or like a certain artist. If you're doing like something, this like literally just like one set of axes, like kind of the first basic plot we created, there's no good reason I can think of why you shouldn't be able to use plt.plot or plt dot whatever instead of like the axes dot whatever, especially if you're just like looking at something. Like you don't need to create figures and axes and then do something from the figures and the axes just to like, you know, change the color or like, you know, make it transparent or something. Yeah, thank you for that link, Anderson. All right, we're kind of right at the end of our time. So yeah.
Thank you, Anissa, and thank you everyone for attending. Please flood the chat with some virtual gratitude for teaching this very complex and unwieldy subject of data visualization. Hopefully you've learned enough to begin learning what you want to do in your plots moving forward and to make some of that happen. Thank you again, Anissa.
Thanks.